high, the 6.4, the correlation. So I introduced the 3 types of correlation. The first one is Pearson's correlation coefficient, R. So this is the most common correlation coefficient. Usually we say correlation, so that is Pearson's correlation. And second one is Spearman's correlation, that we use the rho for this textbook. And that is a kind of non-parametric version. So for example, that we can use that for the rank of the observations or something like that. So it's robust against outliers, and we don't really have any distributional assumption to see the meaning of the correlation. And the third one is the Kendall correlation, TAL. So that is similar to Spearman's correlation, but the slightly simpler definition. Okay, so Pearson, Spearman, and Kendall. And here we study Pearson's correlation first. So the Pearson's population correlation coefficient between 2 variables, x and y, that is defined by this quantity. And so this quantifies the strength of linear relationship between x and y. So maybe it's good to see the examples first. So Pearson's correlation coefficient is basically 1 if x and y have perfect relationship. Here, the x-axis and y-axis are missing, but you can assume that for every figure that we have x and y. And if x and y has perfect relationship, that means that all points are on the same line, then Pearson's correlation is 1. So that is the same for this one, this one, this one, regardless of the slope. If slope is negative, we say actually the Pearson's correlation is -1. And in the middle, if we have some strong relationship between x and y, positive strong relationship, but still we have some noise, then Pearson's correlation is lower, 0.8, or even the smaller correlation, 0.4. 0. So this is just the random. X and y are independent. And negative relationship, we have the negative, the Pearson's correlation. And correlation of 0 means that we have no linear trend. So if we make a trend line, it's either flat or it does not exist. So no relationship such as x increases, then y increase, or the x increases, then y decrease. We don't have such relationship for these figures, but still there are some patterns. Clearly, that we have some maybe quartic pattern here, and we have some pattern here. I don't know how to say it, but it's all points are on a square, tilted square. And this is quadratic pattern, and this have the combination of 2 quadratic patterns and the circular pattern, and we have clusters. So no linear relationship. Still, we have some non-linear relationship. The all correlation coefficient is 0. So what's the definition? Correlation coefficient. Pearson's correlation coefficient's definition is covariance of xy divided by the square root of variance of x times the square root of variance of y. So by using expectation symbol, that we can write this way. So the denominator is a kind of the to standardize the quantity. So the numerator is most important quantity, and the numerator is actually the expectation of the inner product of centered vector of x and the centered vector of y. So inner product explains the relationship between the 2 vectors, and here we have the same idea. But the expectation disturbs because when we just want to know the relationship between x and y, the location doesn't really matter. So we centered x and we centered y also. So essentially, R is defined by this so-called covariance. Okay, so correlation coefficient for sample. Okay, so variable x and y, for example, weight and height, we have some true the correlation coefficient, but we can only observe observation samples, and based on the sample with finite observations, we have to estimate the correlation coefficient. So in this textbook and lecture, we use the R hat to represent the sample correlation coefficient. Sub xy over sx times sy. S sub xy is the estimate for covariance. So just the summation of xi minus x bar times yi minus y bar over n minus 1. And S sub x is the standard deviation. So just the square root of the sample variance. And S sub y is defined similarly. Then we have also another formula for the variance here. Yeah. And S sub xy is called sample covariance of x and y. So the one reason that we define variance by sum of squares is that we can easily generalize the concept to covariance. For example, if S sub x is defined as summation of xi minus x bar absolute value over n minus 1, then it's harder to generalize it into S sub xy. So that is one reason that we defined the sum of squares in variance. And some other expressions. So anyway, we use computer to calculate it. So I don't really care about this. But yeah, at first, the n minus 1 can be canceled. So that is a kind of trivial. And also, with some algebra, that you can prove that S sub xy is summation of xi minus the summation of xi times summation of yi over n. Yeah. So this is just the just expand this term xi minus x bar times yi minus y bar. Then, for example, the term of xi times y bar, then take summation over I. Then we have summation of xi's. And that becomes n times x bar. And using that property, then we can simplify the expression and we can get this. If you use, so if you want to calculate sample correlation by hand, maybe this is slightly faster way. Equation 13 is slightly faster. Yeah, and this is the graph again. And some properties. R is always between -1 and +1. Yeah, so another way to put this is S sub xy is always less than S sub x, S sub y. So this is basically comes from the Schwarz inequality. Probably, maybe you have proved the inner product of x and y that does not exceed the product of absolute value of x and the product, the product of absolute value of x and absolute value of y. I mean, the Euclidean lengths of x and y. And we have basically the same proof for this. And R is equal to 1 if xi and yi have perfect positive linear relationship. That is, that all points are on the straight line with the positive slope. R is positive if xi and yi have positive linear relationship. That means xi increases, then yi tends to increase. Not always, but tends to increase. R is equal to 0, no relationship, but there may be some non-linear relationship. R is negative, xi and yi have negative linear relationship. R is -1, then perfect negative, so all points are on the straight line with a negative slope. So this is true for both R and R hat. And why this property holds? So this is one explanation. So basically, except for denominator, the correlation coefficient is summation of xi minus x bar times yi minus y bar. And the sign of each component, so ith component, so this product, depends on the sign of xi minus x bar and yi minus y bar. So think about the center of the data. X bar, y bar is the center of the data. And if we have positive relationship between x and y, most observations are in quadrant 1 or quadrant 3. And in quadrant 1, the xi is larger than x bar, and yi is larger than y bar. So this is basically positive, positive. So product is positive. And in quadrant 3, the xi, maybe this time xj is less than x bar, so the first term is negative. And the second term also, the yj tends to be negative. So both are negative. So this point is negative times negative, so positive. So that means for most observations, xi minus x bar times yi minus y bar is positive. Maybe some exceptions here, but anyway, we take summation. So overall, the correlation coefficient, sample correlation coefficient becomes positive. And the negative case, the other thing, the other way around happens. So most observations are rather in quadrant 2 or quadrant 4. And for example, in the quadrant 2, the xi is smaller than x bar, but yi is larger than x bar. So these points, this is negative times positive, so that is negative. And quadrant 4, again, this is positive times negative, so this is again negative. So most points have negative value, so it takes summation, but still it's likely to have a negative value. If no pattern, or even if we have a pattern, it's no linear relationship, then observations are almost evenly distributed in 1, 2, 3, 4. So in such a case, the sample correlation coefficient is around 0. So that is the reason that the properties discussed in the previous slide, the hold for the correlation coefficient.